The question I have is, how do you quantify the grain size distribution of soil? If you recall, in another video, we talked about different types of soil on the basis of particle size. If the average particle size is greater than 0.075 millimeters, we call it coarse-grained soil. Otherwise, we call it fine-grained soil. Within the coarse-grained soil group, we have boulders, cobbles, gravels, and sand, once again depending on the particle size. The particle size decreases as you go down in this list. The shape of coarse-grained soil particles is either round, like this, or angular, like this. The two major classes of fine-grained soil are silts and clays. The clay particles are smaller than the silt particles. The three most common clay minerals are kaolinite, illite, and montmorillonite. The particle size decreases as you go from kaolinite to montmorillonite. The shape of fine-grained soil particle is platy, like this. Here is a picture showing a sample of sand, and here is a picture showing the close-up of three particles. This is an electron micrograph of a sample of kaolinite, where you can clearly see the particles are platy. The montmorillonite particles are platy as well, but the thickness of the plates are so small that they tend to curl up, like you can see in this picture. There are two laboratory tests that are used to quantify the grain size distribution of soil, and these are sieve analysis and hydrometer analysis. So let me first briefly talk about these. So let's start with sieve analysis. Say you just brought a sample of soil from the site that you're working on, and you are interested in finding the particle distribution in the sample. What do we exactly mean by particle distribution? Well, if I zoom in on a small sample of soil, I'm going to see some silt-sized particle, some gravel-sized particle, some sand-sized particle, and some clay-sized particles, right? Among the sand-sized particle, some may have a diameter of 2 millimeters, some may have a diameter of 3, some may have a diameter of 4, and so on, right? So the bottom line is there's a range of particle sizes in this soil. Supposing, say, this is our range, 0.5 micron to 10 millimeter. According to some of these classification systems, we'll talk about them more precisely in a little bit. If the particle size is greater than 4.75 millimeter, is called gravel. And if the particle size lies between 75 micron and 4.75 millimeter, it's called sand. And if it lies between 2 micron and 75 micron, it's called silt. And if it's smaller than 2 micron, it's called clay. So one of the questions we are trying to address is, what are the percentages of clay, silt, sand, and gravel in the soil? But this is not enough for us. We want to divide this range into a number of smaller intervals and find the percentage of soil in each interval. Then we can plot the particle size distribution in a smooth curve and learn a little bit more about that distribution. We use two different tests to achieve this, sieve analysis and the hydrometer test. If you recall, this is the particle size that separates the coarse-grained soil from the fine-grained soil, right? So it turns out that the fine-grained soil stick to the wire mesh of sieves and clog up the holes. And therefore, you cannot use the sieve analysis to find the particle distribution within the fine-grained portion of the soil. So we use a different test called hydrometer test. This is based on the Stokes principle of a particle falling in a fluid. We'll talk about this a little bit more later. So this is what we do. We stack up a set of US standard sieves like shown in this picture. The size of the wire mesh opening decreases as you go down. You place the sieve with the wire mesh opening of 4.75 millimeter at the top, 0.075 millimeter opening at the bottom. In US standard sieves, this diameter corresponds to number 4 and this diameter corresponds to number 200. So the amount that is retained at this top sieve is the amount of gravel in the soil. The amount that passes through the bottom sieve is the amount of fine-grained soil. So the whole thing is attached to a shaker, which when turned on will sort the particle according to their particle size in these different sieves. Then you take the sieves out and weigh them individually and figure out the amount that passes through each of the sieves in the stack. Then you plot the results on what is called a grain size distribution chart or a particle size distribution chart shown over here. The horizontal axis has the grain size in millimeters increasing in this direction, right to left. And on the vertical axis, you plot the percentage of soil by weight that passes a sieve of a certain diameter. So for example, this point over here corresponds to a US sieve number 10. And if I draw a horizontal line over here, and it cuts at about 95%. So what that means is 95% of the soil passes through US sieve number 10. Another way of saying that is 95% of the soil is finer than a diameter equals 2 millimeter. So let's pretend that this is the curve we got from the results. But let me point out the following first. Now remember, the sieve analysis is done only on the coarse grained portion of the soil, right? So only this part of the soil up to this point is obtained from the sieve analysis, and this remaining part comes from the hydrometer analysis, which we haven't even started talking about yet. So let me do that next, and then we'll come back and talk about this curve a little bit more. So this is the basis for the hydrometer analysis. You probably learned this in your fluid mechanics course. If you put a sphere in a cylinder full of water, the sphere is going to start falling, and at some point it's going to reach a steady velocity, and that velocity is given by this equation according to Stokes' law, where v is the falling velocity, d is the diameter of the sphere, rho sub s is the density of the solid, mu is the viscosity of water, and rho sub w is the density of water. So if I keep the fluid and the material forming the sphere the same, then the velocity is a function of the diameter of the sphere. And therefore, a large diameter sphere will fall faster than a small diameter sphere. So this is the basis for the hydrometer analysis. Say initially you start with the cylinder full of suspension of the fine-grained soil and float what is called a hydrometer in it. The fine-grained particles will start falling, with the larger particles falling faster than the smaller particles. We start with the uniform suspension in the beginning, but with time the density of the sediments will increase in the vertical direction. Because the density of the sediment becomes smaller and smaller in this part of the fluid, the hydrometer will become more and more immersed in water. So by keeping track of this, with time, it turns out that you can calculate the particle distribution in the sediment. I'll let you refer to a book for full details of the analysis involved in extracting the grain size distribution of the fine-grained part. Let me bring that grain size distribution curve from the previous slide and talk about some quantitative information that we extract from the grain size distribution curve that will later be used to classify the soil. First, we need to know the percent fraction of soil types. So this is what we do. This vertical line divides sand from fines, right? And this vertical line divides gravel from sand. So what we do is we draw a vertical line and then take that point, the point where the vertical line intersects the curve, and find the percentage corresponding to that point. And similarly, we take this vertical line and find the point that vertical line intersects the curve and find the percentage at that point. Then, finding the difference in the percentages between the 2 points, we can find the percentage of that particular soil. Okay, so let's go ahead and find the percentages of different types of soil. And we see that 100% of the soil is finer than the diameter corresponding to this vertical line, and therefore the percentage of gravel in the soil is 0. As per the sand content is concerned, this is 100, this is about 3, so 100 minus 3 is 97%. 2 micron is the dividing diameter between silt and clay. And if I extend this curve smoothly, it's going to cut the horizontal axis over here someplace. And therefore, the silt content is 3 minus 0, which is 3%. And there's no clay in the soil. 2, we extract some information about grading. First, a little bit of qualitative discussion. Supposing, say, we have a soil whose grain size distribution curve is given by curve A. So what do you guys see from this? See, the amount of sand in the soil is almost 0. In other words, the difference in percentages between this point and this point is almost 0. So there's plenty of gravel, there's plenty of fines, but there's no sand in the soil. Such a soil is called gap-graded or skip-graded soil. Say we have another soil whose grain size distribution curve is given by curve B. So what do we see here? First, we see that 100% of the soil is sand and its diameter lies within a very narrow range. In other words, it's a uniform soil. So we call this a uniformly graded or poorly graded soil. So let's consider a third soil whose grain size distribution is given by curve C. And we see that there's a little bit of everything in the soil, and we call such a soil as well-graded soil. So the large pores between large particles in the soil will be filled with small particles. And such a soil will have a high strength and low permeability, and such a soil is a desirable soil. So the next question is there a more quantitative way to identify these? So it turns out there is. So let's first define 3 diameters called D10, D30 and D60. So if I come back over here and draw a horizontal line at 10%, the diameter at which the horizontal line intersects the grain size distribution curve is called D10. So D30 and D60 are similarly defined. So I picked up these diameters for curves B and C. So let's calculate the ratio between D60 and D10 for the two curves. And I got 1 for curve B and 50 for curve C. Now remember, soil with curve C is supposed to be a well-graded soil, and soil with curve B is supposed to be a uniformly graded soil, right? So the drastic difference in these numbers suggests that this ratio could be used to quantitatively identify these. In fact, this is what is done in the Unified Soil Classification System. So this ratio Cu is called the uniformity coefficient. The Unified Classification System also uses another quantity called coefficient of curvature, C sub C, which is defined like this. So this quantity basically says whether a given grain size distribution curve is concave or convex. To sum, these are some of the properties that I use to quantify the grain size distribution of a given soil. The percent fraction of soil types, C sub U and C sub C. In another video, we'll talk about how to utilize these quantities in classifying a soil.